I'm Nathan Hara.
I'm Kevin Leonard.
And our project was to build a 3x3x3 LED cube. So when we turned in our proposal, our initial requirements were for us to construct a 3x3x3 cube using blue LEDs, which came to a total of 27 LEDs. We were going to implement a multiplexing system using transistors in order to control the LEDs for the cube. Then we would then interface the cube with the Nexus 2 board, and then we would create firmware to implement various lighting patterns for the LED cube. But as we went through our design and construction of our cube, we found out that we were able to create a 4x4x4 cube using a total of 64 LEDs. And this was because we used MOSFETs for our transistors, which increased the efficiency of our multiplexing system. And then a feature that we added was adjustable speed variation within the light patterns in our LED cube. And so our system block diagram is just like the other projects that we've been using. We have 3 GPIOs. We use Nexus 2 buttons and Nexus 2 switches to control light patterns and speed variations for our light patterns. And then we also have our LED cube, and this is just one layer of our LED cube. So from our cube control GPIO, we have a bus that controls the layer and which column of the LED to turn on the LEDs.
So as Nate kind of talked about, the different layers within the cube are controlled by the NMOS, which connects all the cathodes within one layer. So the 16 cathodes are connected to one NMOS, and then all the anodes for a layer are connected to the corresponding LED above it. So there's columns connected together, so 16 columns and 4 layers. That one didn't show up, but basically, to operate it, you would provide a gate voltage higher than the source on the NMOS to activate the MOSFET, which would allow current to drain down to ground. And then if you put a voltage high enough for the LED to activate, you could open up this side and then basically get current to flow through that particular LED, and it flows through this layer, not the layer above, because this layer is off. So that's basically the idea of controlling which one you're going to use by not having 67 outputs, because we only have 20 outputs right now. So the multiplexing idea is to use tying all the cathodes together and all the columns together to greatly reduce the number of outputs, because as the cube grows, it just becomes enormous. So current flows through, you light up that LED, and then basically to switch the whole system upside down, you can flip the voltages and turn on the other layer above it. And basically this will only have one layer on at any given time. So to make it appear that 2 layers on at once, you would just switch back and forth between these at a rate that your eyes perceived them on to be at the same time. So that's the multiplexing system. And then the testing integration, our original design used BJTs, but BJTs were chosen to, as the system grows, you can greatly reduce the number of outputs using the 2 BJT design. But there was an oversight, is that the blue LEDs require at least 3 volts to light up to maximum intensity, and the silicon drop across BJT with the 3.3 volts out the Nexus board will only ever allow you 2.6. So LEDs were only just barely on. So it was back to the drawing board, and we came up with a new design using the MOSFET, which doesn't have a drop nearly across it. You just have to supply the gate voltage large enough, and then it behaves just like a switch. So we got rid of the top one and just connected it straight into the Nexus board. So now you have 3.3, and they're plenty bright now. And this eliminated all these BJTs, so now we only have 4 MOSFETs, and then everything else connects right to the Nexus board. So with the reduction in components, we were able to implement the 4x4 and exceed our expectations. So now we can check it out in the demonstration over here. So they're plenty bright to operate with the lights, but it's even more impressive with the lights off, so nobody minds. Kill the AC. But so the software allows for, when you enter into the program, the wait stage in the state machine is that if there's no inputs on the switches, it'll just flash this one LED. And then switch 1 on the bank will enter in the first light show, which just iterates through the layers and then cycles through that after it completes the show. So the software we have now, we included 4 shows for this demonstration. And then switching to the second switch, we'll go to a pattern for rain simulation, kind of. And it'll go through each column showing how to multiplex do that. And then the third one, it's kind of a snake pattern, which goes pretty slow, so you can follow it around. That'll just loop through. And the final one that we included was the explosions of expanding cubes. And that'll go through and switch to different corners and then expand out to the full size. And it goes pretty slow so you can see what it's doing, but this one allows for the speed variation. So if you hold down button 1 and then reset the machine, you can increase the speed and go through the show that way. Or there's a slower one by holding down button 4 and resetting the machine. Well, that's the base speed. So button 2 is the slower speed. So you can really see it iterating through all the patterns. But everyone likes the fast one the best. So, and then if you go to the 5th switch, you would iterate through all the different shows in a loop, one at a time. And basically, the sky's the limit with how many shows you can program, just taking the time. So
one problem that we did run into was we started, as we added more programs, more light shows, we had to add more RAM.
The more memory, because
memory.
The programs just became enormous
Yeah.
when you were controlling individual LEDs at a time. But once we figured that out, it came together pretty well.
Mm-hmm.
So that's it.
Awesome.